If you remember, we started this chapter talking about sequences in general. Then we zoned in on just arithmetic sequences, which are those that you add the same value every time to get from one term to the next. Today we're going to look at geometric sequences. Geometric sequence is one in which value of each term is attained by multiplying the previous term by a constant value. Remember, in the arithmetic, we added a constant term. Now we're going to multiply by a constant term. This value that is called the common ratio. So the constant term we multiply by is called the common ratio rather than the common difference this time. And so we abbreviate it as R, or symbolize it with R. In the sequence 5, 10, 20, 40, then you can see that the first term is 5, and what I've done is multiply times 2 to get 10, and then times 2 again to get 20, and so forth in order to complete the sequence. For any geometric sequence, the next term is the previous term times R. So the u to the n plus 1 is equal to u sub n times R. Once again, this recursive formula like this is fine for finding a few terms, but for the 100th term, we really need a general formula. So we'll look at a pattern. You should see that it's somewhat similar to the pattern that we saw in the arithmetic sequence, except to get u2, we do the first term times R. So to get the third term, we do the second term times R, which is the first term times R. So now times another R, we get the first term times R squared. If we do it again, we get the first term times R squared, which is the third term, times another R, so we get the first term times R cubed. To get the fifth term, we're going to do the fourth term times R. Well, the fourth term was the first term times R cubed, times another R gives me first term times R to the fourth. If you follow this pattern just like it was in the arithmetic, where we would start with the first term and add n minus 1 times the difference, this time we're starting with the first term and we're multiplying times that ratio raised to the n minus 1 exponent. So, for example, I want to find the 10th term of this series. So I'm going to find the 10th term. I'm going to take the first term, 2, figure out what R is. Well, to get from 2 to 6, I multiply by 3. And for the 10th term, 10 minus 1 is 9. So for the 10th term, I get an exponent of 9. When I multiply that out, I get 39,366. This problem's a little bit different. It gives us the first term and the fifth term, and then it wants us to find the common ratio. So we can't just see what is being multiplied each time. We're going to have to solve for it. So I'm going to start with u to the fifth term, and I know that that's going to be u to the first term times R to the 5 minus 1, or the fourth power. So notice where I'm getting this. Since this is 5, this is going to be the fourth power. So 512 is equal to 1250 times R to the fourth power. So to get R by itself, I'm going to divide 512 by 1250 to get R to the fourth power. I'll simplify this. This is 256 over 625 is equal to R to the fourth power. Remember, I can get rid of my fourth power by raising it to the 1/4 power. So 256 divided by 625 to the 1/4 power will be equal to R. And that comes out to be 0.8 according to my GDC. And we know that that is 8/10 or 5/4. So R is equal to, 4/5. Got turned upside down there for a second. For the geometric sequence 3, 15, 75, find the least value of n such that the nth term is greater than 150,000. So my nth term needs to be greater than 150,000. Well, I would get my nth term, remember, u to the first times R to the n minus 1. That would give me my nth term. And so this needs to be greater than 150,000. So 150,000 is less than u to the 1, which is 3, times r. We notice that we're multiplying by 5 to the n minus 1. So now to solve this for n, I'm going to first divide by 3. That gives me 50,000 is less than 5 to the n minus 1. Well, I have my n as part of an exponent. Remember, we can use log or natural log. I'm going to use natural log of 50,000 is less than the natural log of 5 to the n minus 1. Following our logarithmic rules, our rules of logarithms, that means that n minus 1 is equal to, or times the natural log of 5 is the same as the natural log of 5 raised to the n minus 1. So now I can take that natural log of 50,000 and divide it by the natural log of 5. That will be less than n minus 1. When I do this, this comes out to be 6.72 is less than n minus 1. Adding 1, 7.72 is less than n. So the first n greater than the least value of n that's greater than 7.72 would be 8. So n equals 8 would give us that value. Find the 30th term in the sequence. So this one is for you to try, so you need to pause the video and work it, and then you can come back and check your answer. Okay, we start off with the first term, so u30th. The 30th term is the first term. Looks to me like this has been multiplied times 3, and I need to do the 29th power since it's 30 minus 1. And when I use my GDC for that, I find that that's equal to 2.75 times 10 to the 14th power. So 3 significant digits, and then this is written in scientific notation. Okay, it gives me a first term and it gives me a fourth term, and I'm looking for the common ratio this time. So we know that the fourth term, 104, is equal to the first term, 832, times r raised to the, if this is the fourth term, then I need 4 minus 1 or 3. So 104 divided by 832 is equal to r cubed. When I reduce this fraction, it turns out to be 1/8 is equal to r cubed. So I can take the cube root of 1/8 to get r, and that is 1/2. So r is 1/2 in this case. We have one more example we need to look at here. For the geometric sequence 4, 20, 100, and it looks to me like what we're doing is multiplying by 5. So r is going to be 5. I want to find the value of n such that the nth term is less than 200,000. So 200,000 has to be greater than. So this time it's less as compared to our example of the first term times r, which is 5, to the n minus 1. So once again, I divide by 4. That gives me 50,000. And then I'm going to have 5 to the n minus 1. Once again, we'll do the log or the natural log. It doesn't matter which one you do. Natural log of 50,000 is greater than the natural log of 5 to the n minus 1. So the natural log of 50,000 is greater than n minus 1 times the natural log of 5. Dividing both sides by the natural log of 5, natural log of 50,000 divided by the natural log of 5 is greater than n minus 1. We said that this was 6.72, I believe, which is greater than n minus 1. So we add 1, 7.72 is greater than n. The first integer less than 7.72 would be n equal to 7. So this is the work we're doing on those pages. And also for homework, I want you to watch the lesson 6.4 video.